Okay, so do we have Joaquim here? So our next talk will be from Joaquim Castella Triginer from Virtual Vehicle Research. And the title of the talk is Enhancing Safety with RISC-V-based Spider Autonomous Robot, a use case from the ECSEL Fractal project. So please go ahead.
So, thanks. Perfect. Thanks, everyone, for the attention. I want to introduce what we did and what we present. So we wanted to enhance safety using this RISC-V architecture and based on within our robot, what we call a spider. It is a testing robot. When we have whatever other functionality on the automotive, we use the robot to test the specific functionality, and that is included in the use case of Fractal, this ECSEL Fractal project that I'm going to present. So as you said, my name is Joaquim Maria. I come here in representation of Marcus Postel, that is my colleague who was in charge of Fractal project, and he was the use case owner and take care of. But as well, I want to thank Personal Supercomputing. They did the safety services, so thanks to Michael Fernandez, Feng Chang, Sergi Alcaida, Ramon Canal, and Jaume Abella. What I'm going to present is 4 blocks. First, introduction of what is Fractal project. Then, introduction of our robot, what we use for testing this functionality as a spider. A bit of overview on the safety and security in automotive, even though I will focus on safety. And if you have more questions later on for security, of course, I can address that. And then the safety services we implement on the specific functionalities on the spider. Fractal project, a bit long the title, a cognitive fractal and secure edge-based on a unique, open, safe, reliable, low power hardware platform node. Okay, I still have air to define the project, so I want to address 3 main keywords. The part of cognitive, so it's the science who analyze how our brain gets the information, interacts, storage, and that's how we want to, in Fractal, be implemented. So we want how a system could be adapted to external changes and how the system can interact with other systems. And here's a part of the Fractal where it comes. This Fractal is part of these regular structures that are repeated in different scale. In the nature, you can find a lot of things like turbulent fluid or something like that. Geometries, there's a lot of, if you Google, you will see that. But that, at the end, is what in the project helps to implement, for example, cloud applications until a small sensor box in the automotive. You will see here in the next slide a picture that could be a bit more helpful. And then the part of security, I think that there's no much to add. Of course, Fractal has 4 objectives. This part of the open, safe, reliable hardware platform. In the project, it's used 4 hardware platforms. We use the Noel 5 with RISC-V implemented, but there's as well Shilin, CAB6, and I have it somewhere here, and this pulp platform. And this is across to a multi-domain project, so has as well use cases addressing automotive, train, industry, logistics, smart cities. So it's a really big project. and the scope is quite broad. Then we want to guarantee extra functional properties, and that comes safety in place, dependability, timeliness, but of course security and energy efficient. Of course, will be systems that handle maybe basic signaling, but we have large amount of data, so we want to evaluate and validate data analytics with AI. And then we have to integrate fractal communication and remote management features into the nodes. This is the overall project. It's a 3-year project, now ends, I think, by the end of summer. So it's still ongoing. If you have more interest in the project, you can Google Fractal. I think there's here the link, and you can check it. Good. Spider, what we call a spider. At the end is an autonomous robot that has this freedom of movement on the wheels. And we use that to install different sensors, use it for ADAS in automotive. We have this robot here, but we have this sensor box, and here we can put whatever, a stereo camera, or for example, we have the leaders, the configuration. I will explain these 4 leaders in the corner. And we want to cover these 2 objectives, co-execution of safety relevant, security relevant, and as well AI-based tasks, and guarantee extra functionalities or fail operational capabilities. Whoa, good. This is a spider. It's based on this ROS middleware. It is really useful for us to include different sensors and to try to analyze multiple data. Then we have, from the Selene European project, we had the FPGA board that was this Noel 5 and RISC-V implemented there, and we use it for execute our functions. And then you see here the use case architecture with these 4 leaders that give us this cost map if there is any object in the front of the card, and then the collision avoidance can recognize it. So we have these 2 functionalities, collision avoidance and pet tracking. I think that both are really easy to understand. Pet tracking could be really trivial in the sense that it goes from A to B, but then if there's a collision, it's an object in front and so on, has to recalculate. So we have an AI model to execute on time all these recalculations and so on. So we want first the redundant and execution of AI models based on this pet tracking, And then there is the collision avoidance, that is, we want to focus on this redundant execution and how we monitor a RISC-V course. Good. Now safety and security, as I said, I will focus on safety, even though security as well on the On the automotive, there's as well now a standard for 2 years, ISO 21434, and this is our basics, even it's not quite mature. But in safety, we have a standard ISO 26262, now for more than 2 years, a second edition, 2018. With the standard, give us this bit development that we can really analyze the different activities during the development process. And what is important more in the part of the concept, can analyze the different functionalities of a vehicle and get a risk assess, so obtain the risk of those functionalities and set up what is safety relevant and which are not. And within this safety critical, so within this safety risk functions, we have those that are more critical than others, and this is classified with this ACEL A from ACEL D. When we go for these automated driving functionalities, it goes higher ACELs, so it's a higher risk, and we want to cover those functionalities with fail operational capabilities. because they are safety criticals, and we want them to not lose functionalities while they are operating. And for that, we do it with these fail operational capabilities, but at the same time, we want to control wherever failure occurs. And what is important to control such failures like common cause failures, that is one of our main analysis for these safety services. So when we have a single specific event or root cause, we want to avoid that, and we want to achieve with safety properties that we do not have this specific root cause of whatever event that is predicted. And we want to address that with safety mechanisms. In this case, we have the redundancy that helps to parallelize that, and we have the diversity that guarantees that the development process and somehow it's different, so running different hardware, software, and so on. Of course, that would be in a perfect safety world, two independent systems, but when we are in the automotive industry, the cost is really important. So we have to find strategies within our same hardware and software to run strategies to cover that. And here is where it enters what I will present now later on. And then there's this part of monitoring that is as well relevant, because in safety, while doing the concept phase, and once we know that the functionality is safety critical, this functionality you need to calculate will be the time between a fault occur, a failure happens, and then you have an accident. And you want to address this when a fault occurs that does not come to a failure. And this is the strategic time when you want to address and to put there safety mechanisms to avoid that. And now we'll jump to the safety services. This is the part of the personal supercomputing, and the idea behind is to have a functionality that we then add these two properties, the diversity and the redundancy in a library. And here, when, for example, we have our functionality, then this functionality is encapsulated to a wrap function that they designed, and then takes this harmonize these inputs and outputs, create independent copies of inputs and outputs, and execute in a diverse and redundant execution. So we have here the example of two cores and different instructions, and the idea here is that they execute specific instructions in a separate manner, that then we can compare the results and match them. And if there's a mismatch, then of course the safety measure can be implemented. This is the part of redundancy and diversity, but as well you have to control that this process, it's within this time restriction that you have. And that's here important, this multi-core timing interference monitor, that then when you execute the functionality, you are in a top layer on the application layer. And you will run that in the hardware part. So there's a lot of layers in between that you have to guarantee that those execution times are performed in the correct manner. And here's why this edge is important, when you can really trace like the interference, quota allocation, measure total execution times, measure interference of each core and acceleration, and interrupt signal per core. And all this information can be put it in this HCU driver, take it and somehow analyze, and if there something, a fault occur or whatever, computational time is not correct, then you can address it. And these are the final of my presentation, and if you have questions, I hope I could answer.
Okay, any questions? All right, the presentation was complete. So let's thank our speaker again.